Hello, in this video we're going to demonstrate a Allen Bradley SMC3 soft start. Probably the simplest soft start you might see out on the market. I've posted on Learning Hub the quick start manual. It's only 4 pages long, and it is multi-language, and the beauty of this is there's not a lot we have to read to get this thing going. We just have to have a basic understanding. So first thing I want to show is the soft start itself. So this is fairly compact. We can fit it in a standard MCC bucket enclosure, or we could replace an existing motor starter. So it's got an overload built into it, and it's got 3 incoming terminals, L1, L2, L3, and T1, T2, T3 output. And then it's got the terminals here for the control wiring. Here we've got a button, and this would be for resetting it if it gets an overload. You can also set it to reset automatically. And here we've got a dial where we can set the full load current of the motor. So this one goes from 3 amps to 9 amps. But it does have a feature where we can connect a delta run motor, and we can connect the SCR circuits in what's called inside the delta, and I'll show you a diagram of that. So behind this door we have 15 dip switches, and each dip switch sets a certain parameter on how this drive operates. But the parameters are fairly straightforward as long as we have a basic understanding of motor starting. So on the second page, we've got the dip switch settings, or the sequence that we're going to set the drive up. Well, first, and this would be set by dip switch 3, and if it's down or off, up would be a 1, down would be a 0, or off and on. So if we want to use what's called current limit starting, and current limit is when we apply voltage to the motor, we increase the voltage until we reach a certain amount of, or a certain percentage of full load current. Now we know that a standard squirrel cage motor can draw about 600% full load current on starting. So if we want current limit, we're going to make sure dip switch 3 is set off. Now if we wanted soft start, or we call this voltage ramp, where the voltage just increases at a linear rate over a predetermined time. Now some people prefer soft start or voltage ramp. Personally, I prefer current limit. And dip switch 4 and 5, so there's 2 dip switches, and you know from binary, when you have 2 bits, you have 4 combinations. You have 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, and 1, 1. So we have 4 settings, and we can limit the current to 150%. Well, you might ask, 150% of what? Well, 150% of what we set the full load current dial on the front. So I think for the starter, we're going to use the full load current is 6 amps, or for the motor that we're going to connect, the full load current 6 amps. But because we're hooking it up inside the delta, well, we need the phase current, and we can all do the math. 6 amps divided by √3, and maybe I'll set it at about 110, 120% of that. It's close to 4 amps. So I'm going to set the current limit percentage to 350 by setting dip switch 4 off and dip switch 5 on. and the start time, where this is the time that we're going to let it sit at 350 milliamps. But on this particular starter, and that's common for all these compact soft starts, is the reason they can make them so small is because they know they're only going to conduct through the SCRs on starting. They've got what's called a bypass contactor inside. So after the start time has elapsed, it's just a hard contact that closes and bypasses the electronics. So I've set it for 25 seconds, so we'll see how that goes. And that's dip switch 1, 2, and 8. So for 25 seconds, dip switch 1 is on, 2 is off, and 8 is on. So I've set that for 25 seconds. This one's 350. Current limit. The fourth step is if you want a kickstart or not. We're going to be using the same motor and the same flywheel that we used in the Y Delta starter. So it is a lot of inertia. So what the kickstart does, it applies the full voltage, or basically locked rotor current. So we get locked rotor current for a brief period of time. That's just to get it to kick. It's called a kickstart. And that's going to be 450% of FLA. And I've set it to come on for 1.5 seconds. I want a good kick to get it going. It's got soft stop, and this would be for maybe for a pump, where if something's pumping, you don't want to just shut it off and then get some backspin. This will gradually reduce the voltage to stop the pump. I've got that disabled. Again, this was 2 dip switches, so that gave me 4 selections. And this is the soft stop is 2 dip switches, so I can go from I think 1. Yeah, you can go 1 times your ramp time, but I have it disabled. So for off, I want them both set down or to 0. And the dip switch 6 is just for the auxiliary contact. We can either make it come on, so we can turn a running light on. We can make it come on as soon as we apply power to the motor, or we can make it come on when it gets up to speed. I'm gonna set it to up to speed, so I'm gonna make sure dip switch 14 is up. And overload, because this is going to be a hard stop or a hard start, I don't want that overload to trip on me. I know I'm going to put a lot of current through it for quite a long time. So this gives me a class 10, class 15, or class 20. I'm going to set it for class 20, which is, in theory, it means that the overload can have locked rotor current applied for about 20 seconds before it'll trip. So hopefully it doesn't trip. So I'm going to set 11 and 12 both high or both up, and reset. I can make it so it, and this is common for IEC starters, we can set the overload to reset by itself. As soon as it cools down, it'll reset, or we can make it manually reset. I set it for manual, so I set dip switch 13 down. And step 8, and this is what I'm gonna show you on the board. It says, are you gonna connect it to the line or inside the delta? And because the anticipated starting current is gonna be high, and we do have a delta run motor, I'm going to connect it inside the delta. So I'm gonna set it to down. Dip switch 15 is gonna be down, so it's gonna be delta. And then step 9 is just set the FLA of the motor. So again, it's 6 amps. 6 amps divided, that's the full load line current. But if you look at the board, if we look at the board, this is actually what we have. We have our, I've shown each pole as a back-to-back SCR. I'm not showing the gates, but there's there's a gate driver circuit in there driving the gates. We just have to have a basic understanding how that works. But you can see I've connected basically this back-to-back SCR bridge in series with the motor phase, and we know it's connected in delta, so this current is going to be the line current divided by √3. So it's going to be about 4 amps versus 6 amps here. So that way I can drive a larger motor with a smaller drive. Again, if you're supplying these parts for a fixed cost, well, if you can do it with a smaller drive's much cheaper than a bigger drive. So I'm not going to go over the delta connection, but you can study this if you want. But I've redrawn it here, and again, 1, 2, 3, 4, 5, 6. And in red, that is the bypass contactor. So what's going to happen when the ramp time expires, these are going to close, and that'll do the last ramping. Sometimes we can hear it, but sometimes after the ramping time, it probably is up to speed, so we're not gonna see much from there. Okay, so there is our power circuit, and you can study that, but just keep in mind we are connected inside the delta. And I have page, I believe that's the 3rd page, and this is the wiring diagram. And the beauty of this drive is really we've only looked at 2 pages to configure this. So it's got the IEC standard, what you might see on an IEC or a European style drawing. We're looking at the NEMA, so you can see if we hook it up to the line, we're just going L1, we're going to put our incoming L1, 2, and 3 on the top, and T1, 2, and 3 on the bottom. But because we've hooked it up inside the delta, we've got to closely follow this drawing. There are some terminals in the back for changing the fan. If you want to install a fan, we don't have to worry about that. And here it gives us an example of 2-wire control. We should understand what 2-wire control is for. That's for circuits that we want to restart on their own if we have a loss of power. And then we have the 3-wire control, which is what we're using. So there's terminals A1 and A2. We're going to apply 120 volts. This drive uses 120 volt control. You can buy these in 24 volts or even 240. I think they'll work on 240 or 120, but you can buy the DC voltage model as well. 24 volts is very common. So I've just wired 120 volts from A1 to A2, and then from A1 or from the hot, I've got it connected to IN2, and then so basically it wants to see a high signal on IN2 before it will run. So that's the ready signal. And then when if it gets the 120 volt signal on IN2, if you push the start button, you will get the start signal on IN1, and then the drive will start. I've also got terminals 13 and 14. This is like an auxiliary contact, and I can set this to close when I start the starting sequence, or I can get it to close when the bypass contactor comes on. And I've got that hooked up to a run light. Okay, so let's start that motor up. Okay, we've got the same drive setup we've been using for the other demonstrations. We've got our 12 lead Delta Run. So it's got 6 coils, each rated 104 volts. So we've got them connected series Delta for run. And we've got our big flywheel, and we've got the eddy current brake so that once we get it going, we can stop it quickly. But we're not putting any load other than the load of the eddy current rotor itself, but it's not providing any electrical load. So of course we had to run 6 leads back to the starter. And like I said, we've connected inside the delta. I've got the current set at about 4 amps. So that would be the phase current. And the line current is going to be about 3 times that. And we've got the current limit set to 350%. So we've got our amp meter here. Once it starts, it'll stay at the same current until the ramp time elapses. and then the bypass contactor will kick in, but we'll probably be to full voltage. So you'll notice when I turn it on, the current should stay pretty steady, but the voltage will slowly increase. And remember, I've got it connected across the output line, which will go from probably 100 volts up to about 208 when it's the bypass contactor comes in. Okay, breaker on, and here we go. So about 20 amps, 19.9, and it's staying steady. And I have it on the line. I have it on the line, not the phase. So it's pretty steady, and it's about 109 volts. Voltage is going, it's going up slowly, but the current is dead on 20 amps right now. But you can see the voltage is increasing. So it's just adjusting the voltage to maintain that current. And there was that last little kick at the end when the bypass contactor came. It went up to about 26 amps. And it's at 208 volts now. That was a pretty smooth start. In one of the previous videos, we started this same drive configuration across the line. It started in about 10 seconds. Well, I had the ramp time set to about 25 seconds, so it took at least 25 seconds to start it. So what we're giving up in time, we're gaining in supplying it with less current, putting less disturbances on our line. Now, we don't see much because it's a small motor. It's only 6 amps. But if you look at some of the videos we took in the sawmills, these big motors can take hundreds or even thousands of amps.